CLI and a cross-platform IDE for C and C++. Download now.
My name's Andrew Drakeford. I'm going to be talking about data-oriented design, or rather the missing step in data-oriented design. Here's an example of the thing we can achieve sometimes when we take this extra step. We did a leave one out regression performance run. The reference implementation took 14,000 seconds. The new implementation took 18 milliseconds. By exploring the problem context and using some ideas from George Polya about heuristics, we will examine our thought processes and problem-solving approach to identifying better designs. We'll show through examples how we navigate the problem space and can end up with huge performance improvements. Data-oriented design sort of burst onto the core C++ scene at cpponline 14 when Mike Acton gave a talk about data-oriented design. It's hard to summarize his 1 hour talk, but here are some of the key issues that he pumped out. Programs just transform data from one form to another. Understand the problem better by understanding the data better. Different problems require different solutions. Different data implies different solutions. If we understand the cost, we understand the problem better. If we understand the hardware, it helps to understand the cost, to understand the problem. Code is data, everything is a data problem. He suggests that we don't solve problems we don't need or don't have. I think in this case, he's talking about adding too many abstractions. Latency and throughput are not the same. Where there's one, there are many, so solve the most common issue first. One thing that we are going to build on is context. The more you have, the better you can make your solution. NUMA pre-built data extends back to right to the creation process in gaming. You'll have something similar. Software is a real thing running on real hardware, not the pixie dust running on the fevered dreams of computer science PhDs. I think it was something like that he said. Reason must prevail. We want evidence that our approaches are actually having an impact, so that what we do works. Also in the literature, there's a book called Data-Oriented Design by Richard Fabian. If you go to the website here, you'll get to see most of the contents of the book. In the book, Fabian extols the power of ordering of data, and this is a thing that we also recommend. Often data-oriented design and object-oriented design are compared. There is just no comparison between the two. They are absolutely poles apart. Data-oriented design has a focus on the absolute detail, exactly what pieces of data are in play, what functions do they interact with, how do they sit in memory. It's very, very detailed, very, very actualized. Object-oriented design, which has been a popular and successful way of implementing systems, its core principles are hiding information, bait and switch by polymorphism, and keeping the big structure simple and visible by hiding away the details. Unfortunately, this hides away the data transformations and what really happens inside our system, making it difficult to reason about. On top of this, we also have a thing known as Conway's law. The structure of a system tends to reflect the teams that built it. So we have separate teams hiding information from each other inside objects which are hiding information from each other, which do a bait and switch at runtime with polymorphism. So it's not surprising that we can get slowness occurring in OO systems. Some of the many talks that you can see on data-oriented design tend to go for what I call micro architecture optimizations, So using certain language idioms just to try to get things to go a bit quicker. So for example, trash the templates, vilify the virtual, imbibe the inlines, ban the bool, can the caching because we're going to recalculate, love the lambdas, and eviscerate exceptions. However, we're not fishing for minnows. We're not after small percentage improvements, we're after huge ones that we can achieve by having a better understanding of the problem. So what do we mean by a better understanding of the problem? This talk is about essentially a missing step in data-oriented design. We're going to try and explore this very, very highly dimensional problem and add a few more tools in there that might be useful to people. So in real life, the performance of a system is extremely highly dimensional in terms of the choices that we have. We have algorithmic choices, we have different decompositions, we have the choice about whether or not to offload stuff at compile time. We have the spatial layout of the data, the execution ordering, how we're going to vectorize or not vectorize. Can we cache? How are we going to cache? How are we going to order the caching? How on earth are we going to do random accesses without going to outer wilderness of memory? How are we going to do lookups? This is a lot of the physical stuff mixed in with a core sort of pure algorithms thing. But we also have to consider these factors within the context of the problem domain and align hardware efficiency, software efficiency, sequencing, spatial temporal locality of reference. And what we're going to argue or demonstrate is that by considering the broader context for solving the design problem, we can allow and admit sometimes stupendously better answers. In this example, we're going to show how to leave one out linear regression nearly 1 million times faster. So these topics that we have in our design challenge can possibly be grouped under a sort of a logical design, the algorithmic design, a physical, a spatial temporal ordering, layout and sequencing, and also idiosyncratic issues from the problem domain. The problem domain may have its own specific utility function, not a common one. It may have side information and constraints that are peculiar only to it. There could be invariants and specific patterns in the data which we could exploit to get a much more efficient algorithm. So we probably want to have a few more tools. What I propose that we bring in is George Pollier's problem-solving heuristics, Skinner's algorithmic design approach, some Socratic questioning, data orientation, and the vectorization stuff that we will want to see get that extra factor of 10 out if we can scale. Well, first we have to consider the hardware challenge. What we're going to run our software on. We were told that hardware runs on software, and I think he's onto something. This is a graph of the performance of microprocessors versus memory over the decades since it started. And what you can see is there's a huge gap between the performance of, or the increase in performance of the processor and the increase in performance of the memory that it's going to work with. Access to memory is slow, and over the years, it's got a 3 order of magnitude gap. For the processors to work at the kind of capacity that we need, there needs to be a fast memory for them to work with, and the engineers have invented a hierarchical caching structure with very expensive and fast memory in level 1, level 2, and level 3 caches. These have access times of 4 cycles for level 1, 10 cycles for level 2, and 40 cycles for level 3. And you can see that the cache size goes up from 32 to even 100 megs on these monster processors. If, however, we don't get our code accessing in one of the caches, we go to the outer memory, and we could end up spending up to 200 cycles waiting for a piece of data. That's 50 times slower than getting it from the level 1 cache. So that's a huge performance hit. So something that we want to really avoid. So apart from the caching things, modern processors have got fantastic instruction level parallelism. They can execute multiple instructions at the same time. And some of those instructions can be SIMD instructions, single instruction, multiple data. And these can operate on multiple lanes at the same time. So you could have an AVX512 instruction adding 2 AVX512 registers, each containing 8 doubles. So 8 double additions in one cycle. That's a huge throughput. However, keeping things running fast is really a challenge and organization for the processor engineers. And if the processor's pipeline gets disrupted, we can end up with a very serious wait. So what the engineers have done is they've put together schemas for predicting which memory we're going to need and trying to fetch it beforehand, which branch we're likely to take, and maybe speculative execution. The processors have become very stateful because they're running this huge prediction machine so that they can keep the thing going quick. So important processor states are what we hold in the registers, what we hold in the level 1, level 2, level 3 cache, what we hold in the instruction cache, whatever state the predicted bits of the hardware are using, outcomes of branching decisions, where we recently fetched memory from, what functions we recently called. And it's a pretty complicated stateful beast. So we're going to look at some important idioms that can be useful in working with the processor. The core idea really is around memory access, the ordering of memory access, the layout of data in memory, how we're going to do vectorization, and pre-computation. If you pre-compute something, it's really fast because it doesn't run. So, memory access, the power of ordered data. If we lay our data out in a way that enables it to do fast processing, we can use better algorithms. These have better ON and also probably better data locality of reference and better memory usage. So, order your data, use better algorithms. For example, without sorting, a binary search is just an order n search. With pre-sorting, it's a log n, it's exponentially faster. Same with finding pairs, set intersection, removing duplicates, merging lists. If our data is ordered and kept, that order is maintained, we will go a lot quicker. The power of contiguous data. For a start off, if your data is contiguous, sort of, say, a chunk of data held in a vector, typically we would iterate it along the vector, and we would just be making a linear walk through memory. This is very predictable. The hardware device is very good at predicting when you're walking linearly along a long vector, always taking the next piece of memory adjacent to the one that you just took. It performs well. Also, when you have contiguous data, you have a very dense representation. I mean, if you consider a long vector of doubles, it's completely packed with doubles. There's no space. So when we move that memory, we're moving a lot of information. But not only is the information that we move densely packed, we've actually got special instructions to help us move. We've got vectorized instructions which can grab 8 doubles and put them straight into a ZMM register in one go. And if we were to do a mem copy with that sort of thing, this is what happens. This is what the assembly looks like. First thing, it uses a vector move pack double from some data from the RDX plus RCX minus 40 into the ZMM0 register, and then back out to memory in the next line. And if we look on the right-hand side, we see that this thing, when it's operating under 16,000 bytes or so, it's able to do memory transfers at rates of hundreds of gigabytes a second. It's very, very fast indeed. So next we come to the power of contiguous access, which is pretty much the same thing, or very similar. This is a bit of a meme sometimes, this type of function. We have two loops processing a vector of vectors, or it could be a square matrix. The top one is going row major, and the bottom one going column major. We're adding all the elements into sum and returning the value. One of these functions is massively faster than the other. From a logical perspective, you wouldn't think it made any difference, but actually it makes a huge difference. The top one, the row axis, will be going, what it does, first of all, it's selecting array I with the I square bracket, and then it's going to walk along, select the jth, then the j plus 1th, then the j plus 2nd, and j plus 3, j plus 4, all the way to the end of that vector. That is contiguous in memory. The processor knows where it's going, and it can do it quickly. The bottom one, we're going from the jth elements of the ith matrix, then we're going to the I plus 1th vector to get the jth element, then the I plus 2th vector, I plus 3 vector. So it's making a strided movement through memory. So this isn't just about the loop interchange. If you see this in code, you just swap the I and J and you go 20 times faster and you're a hero. But it's illustrating sort of more interesting principles. And if we plot a graph of the matrix size versus the log of the runtime, the direct axis going along the row takes considerably less time. And as we move up from matrix sizes from about 800 to 1600 elements, the performance gap between going strided or going a contiguous walk is considerable. So go the right way with your matrices. If we want to add a level of indirection, so what we can do now is we can generate the paths that we want and store them as a pair, and then load the pair in the bottom function sum with access path. This means we can try putting different access paths in that are not known to the compiler and are fed at runtime for a lookup and see how that works. What we see here is for small matrices with smaller caches, the orange and yellow, the indirect row and indirect column, are both slow and run around about the same speed. But as we move up to larger matrices, we start paying quite a heavy price for this indirect column access. And one final one, we can shuffle the data to make us have random access. This is the top blue line. So we said indirect access through data which is being shuffled. So it is entirely random. It's only marginally slower than the indirect column. But the difference between this type of access pattern is a lot less for smaller matrices. So random access strategies, we should try and avoid them pretty much at all costs. You try and use ordered or sequential across a sorted data set. If we can't avoid a random access in our code, which we probably can't, we're looking something up, instead of looking up a single scalar result, try and look up a vector of results. If we can hoist that lookup out of a loop and pull all the things out that are needed in a vector, that's going to amortize the cost of the lookup over the vector side. Another thing we can try and do to speed up random access is to minimize the range searched in memory. So instead of trying to randomly access over a huge space, try to randomly access over a small array. This will tend to keep the data hot. And then there's multidimensional locality of reference and space filling curves. Memory is mapped onto a one-dimensional structure. So how do we maintain locality of reference when we have 2D data? Consider, for example, this rectangular layout, a typical array style. If you're on one of the lines and you go to the left or the right, you've got locality of reference. So the data is either one number higher than you or one number less than you in memory space. But if you were to go vertically, you have a separation of the in memory at the width of the whole rectangular pane, which could cause cache misses, for example. A space filling curve maps all points in a high dimension into one dimension, but preserves a kind of locality of reference in the one-dimensional space. And you can see this from the following picture. On the left, we have a Hilbert curve, and on the right, we have a Morton curve. If you pick a point and just look at it, and then think you want it to go right or left, the distance between up and down points and right and left on that line are probably going to be considerably less than the distance of wrapping around the width of the pane. So you do get some locality of reference. And this is used for sort of geographic information systems. I think sometimes in linear algebra, people have used Hilbert curves. I've put together a quick example on Godbolt with the Morton curve. This actually works on my machine, honestgov. When I put it on Godbolt, it didn't work. And the Godbolt servers have probably got very, very large caches. So I tried increasing the size of the matrix that I was using, and it would kill the process, just like freeloaders running stupid programs. So it kills it before it gets to exhibit a time saving by using this lookup scheme. But it does work, honestgov. It's a bit of a shocker, but still. Right, the power of using vectorized instructions. Single instruction, multiple data, XMM, SSE2, YMM, AVX2, ZMM, AVX2, 2002, 2010, and 2018 for the AVX512. If we use these registers, we have the possibility of performing an operation at the same site, at the same time scales as a scalar operation, but using element-wise operations on multiple elements. So, for example, if we filled a ZMM register with 8 doubles and we added them together, we'd get 8 element-wise addings in one cycle. So we get a huge throughput boost if we can use these. But it isn't quite so simple. You don't necessarily just press a button, the compiler, and it works. Sometimes you have to work hard to put your data in structures where this can be encouraged. Consider, for example, this physical representation of a student information with my little brass rings, or a struct below it, long ID, GPA, age. And we stored these in a vector of student data, an array of structures. If I wanted to get all the grade point average data out, and I wanted to say calculate the mean, looking at the chain things, I know it would be quite a horrible, picky job to get the data out. And it is for the computer to do that and get that out and put it into one of those 8-lane registers. So we try to convert our array of structures to structures of arrays. I like my little cylindrical things. I can see myself grabbing 8 of these GPAs cylinders in one go quite easily and stuffing them in a slot somewhere. And the computer can do that too. So there are instructions where it could just go to the vector of GPAs in this physics student data SOA and just load it straight up into a ZMM register, like we saw on the moving example. So we have to restructure our data to make it so that it can work neatly with the registers. So we have to partition the data so that values that will be used together will be stored together. And when they're stored contiguously in an array like this, it means that they can be loaded very, very efficiently. Just one load will get 8 elements into the AVX512 doubles, and then we can add PD, which will add 8 of these things together with another register or some multiplication thing, whatever. We can load them in one instruction and operate on all 8 of them with one instruction. But having them together in memory to begin with is a really good idea. You need to do that. If we had derived classes, we'd have to separate these out into different partitions because the derived classes will have functions that are virtual and have different implementations. And because the implementations are different, they're not going to run the same code. And we can't have virtual functions operating on a register. So we have to partition them so that they're going to do the same thing. Sometimes, however, we can get unexpected benefits, particularly I found with loop hoisting and branching conditions. We can separate out we can partition our arrays of structs on the basis of some conditional or some lookup logic. And this can sometimes get amortized. So we'll basically do one conditional operation and it will apply to a whole set of data. This is what happens when you loop hoist a scalar value. Similarly, we can actually partition data sets by some other condition. So on the left-hand side, we're do big stuff if a value is greater than big, and otherwise we do small stuff. But we could partition those collections of data into 2 collections, one with big items and one with small items. Then we have no branching, no masking. We just have applying the function. It's a lot simpler, go through much more easily. If we look up a vector of values only once, rather than looking up a set of scalars multiple times, we can save a lot of time and energy. So consider, instead of having a map with a key to a scalar value, you can have a map with the same key, but to a whole vector of aligned and padded, ready for SIMD use, primitive values like doubles. When we manage objects that are vectors, not scalars, the cost of branching is amortized over the whole size of the vector. So it kind of falls away, and the sort of branching costs in some applications just vanish. I've seen this myself, and it's really rather nice. Sometimes you might even consider more sophisticated caching strategies because you're applying the cost of the caching strategy to a vector of, say, doubles rather than to a single item. And now for the final bit of this, we're going to look at compile time pre-computation using const extra. In machine learning, there's a lot of linear algebra and multiplying matrices together. And that's what drew me to this as an example. It's not a Fourier transform, one that's probably been done to death for offloading to compile time. If we have a sequence of matrices, A1 to AN, and we want to multiply them together, we have different ways we could do it because it's an associative operation. So we could go A times B times C, or A times the product of B times C. The aim of matrix chain multiplication is to find the best order to multiply the matrices in to minimize the number of multiplications. So this is why the order matters. So if we put some sizes to these things and say A1 is a 10 by 100, A2 is 100 by 5, and A3 is a 5 by 50, and we look at the two ways of multiplying, A1 times A2, and then multiply by A3, that works out to be about 7,500 ops. And then we have A1 times A2 times A3, and that's 75,000 operations. If we could figure out the optimal way of doing this multiplication, we could probably save some time. This matrix multiplication could be seen as a tree, a binary tree. But there are a vast combination of binary trees, a sort of exponential number. So how can we solve this problem? Well, it turns out that it's a dynamic programming type of problem. We could define a cost matrix, Cij, which gives the minimum number of operations in multiplying the sequence between AI and Aj, and we could fill this table up from the bottom up using this relationship here. Cij is the minimum of C to K, and then K plus 1 to J, plus an extra term involved in the multiplication of joining the product of Cik and Ck plus 1J. We saw the split points also, and this has time complexity order n cubed and space complexity order n squared. You can do this and get it to run at compile time, and that's why I want to do this. So we've got a compile time dynamic programming example here where we solve this matrix, optimal matrix multiplication problem at compile time. So I've not seen that done before. There's also one where we actually run the example and it goes about 10 times faster. This one actually does run on Goldbolt. The discussion about matrix chain multiplication can be seen in the algorithms book by Gupta et al., chapter 6.5, and there's a reference there so you can get an access to the chapter. Moving on. So that's all the fun with hardware stuff. It is important, but it's not the only bit of the problem. We actually have this highly dimensional design problem. So let's move out of the fun C++ and strange stuff into solving the hard design problem. With a little help from a guy called George Polyer. He used to teach John von Neumann, and he wrote a lovely book called How to Solve It. For those interested in artificial intelligence, Marvin Minsky said nice things about it. Lots of people have said nice things about it. And I can remember reading this as a sort of elderly teenager and finding it absolutely fantastic. In the book, Polyer explains his approach to problem solving. It's a 4-stage process. First of all, you have to understand the problem. You have to clarify the problem. You can restate the problem, ensure that you understand all the terms and definitions and conditions, understanding the data. Now that sounds quite a lot like Mike Acton to me. So the rest of it is, I think Mike Acton really did part one, understand the data. And this is just adding a bit more support into solving the actual problem. The second phase of Polyer is drawing up a plan, identifying analogous problems, solutions that we've seen before, looking at the right tools, how we're going to decompose the problem. Maybe we can try working backwards. Maybe we can simplify the problem. But we're going to get a plan and we're going to execute it. If we execute it diligently and make sure we're doing the right thing, we're going to be okay. Finally, once we've solved the problem, we can reflect see if there's any of those results that we can take further forward with us, and how we can improve our game going forward. An alternative to understanding the problem from Skinner's book is, what's the input, what's the output? Can I do a worked example by hand? How accurate or optimal must the result be? You don't want to oversolve. How big's the data? All data, also a whole load of data questions. How important is performance? What type of problem is it? Is it numeric, graph, string, set, geometric? Poly is, what's the unknown, what's the data, what's the condition? It's a very sort of mathematical approach. Is it possible to satisfy the condition? Well, we hope so, because the thing should be running and we should be measuring it. Is it sufficient or redundant or contradictory? Maybe this isn't particularly useful. But the next line is, can we separate various parts of the condition, the definition of our problem, and write them down? And for me, the bit that he brings out is, can you draw a picture? Now, this I find awesome. I took this on board, and I've been drawing pictures all my life, and it's helped me immensely. The YouTube tech lead guys are probably too fast typing out the answer to their algorithmic problem to draw a picture. But when it comes to the absolute pinnacle of what the DNA in our species can generate, look at these drawings by Clerk Maxwell, Leonardo da Vinci, Richard Feynman. Oh, and let's just polish it off with Newton, Einstein. These guys draw pictures when they solve problems. Think about it. So, yeah. Devising a plan. This is where the Polya stuff comes to its fore. It has a whole range of strategies. What we're trying to do here is try to find the connection between the unknown and the data, and possibly solve simpler auxiliary problems if we can't get any purchase on the solving the exact problem. Have we seen the problem before? We should say, did we solve it? Do you know a related problem? Have a look at the unknown. Have you ever seen problems which have these unknowns, or data produce the same processing? Can we use the same solution approach? This last one is very important. This one works for me a lot. Can you restate the problem differently? Can you dig back into the problem, into the definition in minutiae? Can you rephrase it? This restating the problem has been found to be a very good way of breaking functional fixedness in some problem-solving cases. Because, again, trying to solve a related, easier problem, an auxiliary problem, can we relax the constraints? Can we make it more general, more specific? Can we change the inputs, the outputs? Does this bring us any closer to a solution? Have you used all the data? This is not just an exam question. In an exam, you use all the data because you're supposed to answer the problem in a certain way. In the real world, if you use all the data and all the notions, you're going to be much more positioned in finding a really, really good answer, adding extra constraints to the problem. So, and finally, heuristics, strategies. Can we reason by analogy? Does that help us? What decomposition can we have for our problem? Can we generalize it? Can we specialize it? Can we look at the end and work backwards? Can we create auxiliary elements, constructions, diagrams, notations, intermediate goals? And a really good one, particularly from Skane's book, is reduction. Can I transform this problem that I don't know how to solve into a problem that I do know how to solve it in that way, and then transfer the results back? He does a lot of ridiculously clever stuff, taking difficult problems, turning them into a graph problem, and then translating them back. Then we execute the plan, test the results. Finally, we reflect. Polya had a diagnosis process, and he found that failure to understand the problem was the most common cause of failure. So make sure you understand the problem. Another failure occurred from two opposite ends. One is rushing to do calculation or coding when you don't have a plan. You don't know what you're doing. You dive in, you get nowhere. The other one is sitting back, waiting for the idea to come without taking any action. You can fail a bit later on just through carelessness and lack of checking each step. Skinner's book, The Album Design Manual, has an ordered approach to working the problem. And at the end, he has credits to Polya, so it's going to be shooting along the same line. He also has a useful catalog of problems and solutions. So the have you seen it before bit can be speeded up. I'm sure that Polya knew about Socrates. Socrates was the king of asking questions. And asking questions is a way of getting good answers. Here we can look at clarification questions, probing assumption, probing evidence, looking for alternative views, exploring the consequences, and reflecting on our inquiry. So if you think you need to answer questions, look at Socrates' list and develop some. Also, we need to have a positive mindset, and it really helps keeping notes on our thoughts and attempts and processes. If you feel stuck, it's part of the process. Here on this web link is a picture of Polya actually having a problem-solving session with the students. It'll make you feel better. Now we're going to work through an example. This is a leave one out regression problem. About 15 years ago, I was part of a machine learning quant fund, and we were looking for predictive factors to predict the market so we could make better investments. With leave one out regression, what you would do is you'd have a data set, and for each data point, we build a model and forecast the value at that data point. But what we would do is we'd use the entire data set apart from the data at that point. And then we'd measure the difference between the forecast value and the observed value. We'd use this distribution of errors and metrics derived from that to help us work out whether or not this is a robust and stable feature vector for incorporation in models downstream. The model uses a simple, linear, low-dimensional relationship, y equals mx plus c. And because we're doing n fits for n data points, it tends to be an order of n squared. So it's a lot of compute because we had literally millions of factors that we wanted to investigate. To make the regression more stable, we also regularized it. This is just adding an extra I to the matrix, regression matrix. So, understanding the problem. Questions about data size. How big is the data set? Well, we've got millions of these things to do. Typically, the length was a few hundred data points. Performance requirements, as fast as possible, please. Accuracy, make it accurate enough so it doesn't interfere with our decision choices. I don't know what to say about that one. So that was a bit of suck it and see. Have I solved this before? Well, I've certainly written linear regression things before, but not leave one out. We had a library from a well-known analytics producer. We called the least squares function on that. 15 years ago, machine learning and cross-validation and stuff like that was nowhere near as popular as it is today. So the first phase of this is understand the problem. What's the algorithm used and why is it so expensive? Well, the model is y hat equals beta 0 plus beta 1 times xi, y equals mx plus c. Straightforward, straight line. Beta 0 is the intercept, beta 1 is the gradient. It's a little bit different than just regular regression or least squares. Y hat minus beta 0 plus beta 1 xi will give you squared is the least squares. We add an extra term, lambda beta 1 squared on there to penalize large values of the slope. This apparently makes it more stable. In traditional regression maths, we have an X matrix, ones plus all the values of the X points, a Y matrix, all the values of the observed values, a beta matrix of, in this case, the two coefficients, beta 0 and beta 1. and a regularization matrix with just lambdas on the diagonal, in this case, just the bottom diagonal. This comes out as a pretty well-known equation, x tx plus lambda times beta equals x ty. We can multiply by the inverse, so beta, our fit, is x tx plus lambda inverted times x ty. Simples. So why is this thing slow? Well, let's have a look at the essence of our regression calculation. We have the xtx matrices, and inside these we have xi, sums over all the xi's, all over the x squared, and also the xty, we have this sum over all the y values, and the sum over the products of xi and xi and yi. So these are the things which make our matrix calculations slow. Obviously, we've got this inverse thing. This is just very simple. And we have this explicit formulation. That's not a problem for us either. So the plan is we want to identify the slow parts and explore auxiliary problems and reflect on the slow parts and maybe draw some pictures. I like drawing pictures, and solve some auxiliary problems. And then we'll end up with a fantastic new algorithm and we'll all be very happy. Now, this bit, I want you to pay strict attention to this. There's a big lesson here for everyone. This is the slow bit. We repeat it n times, xt, x. We have all these sums across all the xi values and the sum of the squares of the xi values. But we're repeating this n times with slightly different data sets because we're leaving one out. And this is the first xdx term that's introducing this order of n data set length dependence. So it's really slowing things down, as is the xdy. So how are we going to make this faster? What can we do? Well, as a software guy who's done the odd bit of vectorization, I'm thinking, I want to go and do an unsequenced reduction, maybe transform reduce, scale it with Fred, SIMD, maybe CUDA if we get the chance. How exciting. This is going to go really quick. And at this point, if there was a bang, you're dereferencing a null pointer, good things would happen. But apparently that's not the case. What we've done is we've applied an answer to a problem that we recognize, but we haven't fully considered the context. And we're just trying to optimize the inner loop. This hugely restricts the scope of our solutions that we're considering. We have to expand the scope. We have to look at the context more broadly. Instead of speeding up the whole of X, instead of considering speeding up just one instance of XDX, we have to look at speeding up the whole set of these things. That's what we're optimizing. So as an auxiliary question, we're going to look at summing. How do the sum over all the xi values work when we're calculating these leave one out matrices? How does this vary over the whole set? So our auxiliary problem is we're going to look at this sum of xi for each of these perturbed sets and see what's going on. We might not be solving anything, but we will get a good intuition perhaps. And if something over xi doesn't work, maybe xiyi might work. So let's get to it. Let's have a go. We've drawn a picture. Horizontally, we've got our rows, and we're going to sum over those when we've left a value out. So we've got n rows, and we're leaving the value out all along them. What's striking is there's a huge amount of repetition. Let's see if we can narrow this down and ask a good question. How could we reuse the sum of the first row to calculate the second row? It's a simple question. Well, the sum of the first leave one out row is the sum of the leave one out row 0 plus x0 minus x1. And the sum of leave one out row 2 is the sum of leave one out row 0 plus x0 minus x2. This looks a bit fishy. So what you're saying is the sum of a leave one out row is the sum over everything, subtracting the value that we left out. So basically, all we need to do is to sum over the whole row. That'll take about n elements, n operations, and then we have n operations where we subtract one element from that summation to get the sum of the leave one out values. Does this generalize to our sums over x squared, xy, sums over y? Yeah, it does. All of them cost n to produce the sum, and it costs n to produce all of the leave one out. So we can produce these leave one out summations with 2n operations. So our new algorithm is just, first of all, go through, produce a sum over everything, and then go through and quickly generate the leave one out values, and then solve the equations for beta 0 and beta 1. So leave one out vector sums. In this case, sum over the top row, we've got sxi is a sum of x, which is a scalar, minus xi. But if that was a vector of xi, we'd end up with a whole value of a whole vector of leave one out values. And this is what we can do in our implementation. So our new algorithm is to generate the new fits using the closed form of the betas by first of all generating these sums and the leave one out sums in 2n operations, and then evaluate the closed form using it sort of a vector-like form. So we're doing these, solving for beta 0 and beta 1 in a parallel manner. To do this efficiently and stick to contiguous memory layout, there's a little framework that I wrote called drcubed. It has these vectors. They use a memory pool, so there's no allocation, deallocation costs or minimal ones. We've got vectorized math operations, and also they support an interface which makes them substitutable for scalar. Code's available here, and there was a talk at CPBCon 2022. Because it's contiguous memory, vectorization works very smoothly. We can also do transformations, which work very efficiently too. The key vector is called a vecx object. Again, it supports math operations, contiguous, aligned, padded, all the really good stuff that we were saying earlier that we want the processor to be able to operate at maximum speed with. Here's a memory pool that we have with all these aligned vectors. And this is the expression that we want to evaluate. Explicit beta 0 and beta 1 is given by these two equations. Note that the denominators are the same. What we're going to do now is we're going to implement that using the drcubed framework by just, it's just going to be very trivial. It's remarkably trivial. This is the code to do this in a vectorized way. First of all, we define three lambdas: multiply, sum, and square, taking autos, returning x times y, x times x, and x plus y. Then we'd call reduce on data x, so we get the sum of all the values of x, reduce on data y to get the sums of values of data y, transform reduce using a square and sum to get the sums of x squared, and also using a multiply and sum on data xy to get the sum of xy's. We generate the leave one out values. Sx leave one out is sx, either sum of the whole lot minus data x. Sy is minus data y, gives us leave one out sums for sy. We can compute data x squared by timing data x by data x. This will give us a vector where all the elements are xi squared. So leave one out of sx squared is the sum of sx minus data x squared. Similarly for sxy, leave one out. We'll set the lambda to 0, so it's just a regular regression. It doesn't have any real effect on performance. This data size is the size minus 1 because we're leaving one out. In the expressions for beta 0 and beta 1, the denominator is common, so we calculate the denominator. So this will be n times sx leave one out plus lambda minus sx leave one out times s leave one out. That's the denominator. The numerator is similarly trivial to do for beta 1 and for beta 0. And that's it. It's not much code at all. Does it run? Well, this is where it goes really fast. I have perhaps cheated by accentuating the size of the data set, but it goes really fast. It's not going fast because we vectorized it. It's going fast because we didn't do the silly thing and jump to the first answer. It could go faster. We could try some blocking and tiling. We try or a zip iterator. We could try using floats and see if the loss of accuracy made any difference. We could try pairwise reduce to make it more accurate. Does this trick generalize? Yeah, I actually had somebody come up with the same thing in a similar case, not the same problem. He had lots of perturbed sets, and he generated them by generating the whole set and then perturbing each element, and had a tremendous speed up. Reflection. This, I hope, was an important illustration of the benefit of not just trying to optimize the inner loop, expanding the context and trying to understand the problem more broadly. Also, the value of trying a simpler auxiliary subproblem. Yeah, we can also try calculating the examples by hand. I tend to use a spreadsheet. Maybe that counts. An alternate way in which we could have solved this is we could have done an advanced postgrad course in matrix computations using the Van Loan and God book. I've actually got it. I can just reach out and get it, but I won't. And then we would have seen this as some matrix update problem. And we could have walked away thinking, hey, isn't it good to know about matrix update problems? It's much more valuable to know about expanding the context. It's much more valuable to know about Polyer's approach. So the key takeaways I'm hoping that people have got is that data-oriented design addresses a very, very highly dimensional problem. It's not just the algorithm, it's not just the physical, there are also idiosyncratic aspects that if we keep our eyes and ears open, we might be able to find and really get some leverage. Working through the problem space in a structured way by using approaches such as Polyer's can give us a lot of help, particularly when we're stuck and we don't know what to do. There are lots of good ideas there. I think always trying to look about expanding the context when we're in a critical area can help to keep the really good solutions in play. And I am a fan of drawing pictures and looking at ancillary problems. Doing these things is rarely ever wasted time. Hopefully you'll find yourself in a situation where you have an increased understanding of the problem that you're working on someday, and you'll give yourself the luxury of innovating. If you want to use the DR-cubed library for play with vectorization, it's there. But yeah, email me your success stories, because the thing is, most people don't look. So if you're the first person that looks, you get a free shot at having a go at a really good problem. I had hoped to try and fit another example in, but there's absolutely no way I could do that. And so I put one on the back in the appendix, which is a real life problem, and I'll leave it there. Thank you very much.